Hello, my name is Dee, and I'm doing a PhD at the University of Birmingham, working on nature-based methods for wastewater treatment. This mini lecture is an introduction to my PhD and is about treating wastewater with trees or plants and improving greenhouse gas emissions in the water sector. I hope you find it engaging and insightful. Given the climate emergency the world finds itself in, we need to develop and implement more nature-based solutions to global issues. One challenge that requires attention is clean water. How can we clean water more sustainably? And how can we make clean water more accessible? Constructive wetlands provide nature-based, low-cost and decentralized solutions to wastewater treatment. This means that they can reduce greenhouse gas emissions, require less money to operate and maintain than conventional systems, such as activated sludge processes, and clean wastewater for isolated households. Currently, there are different ways of designing constructive wetlands, with each design providing slightly different advantages across varying climates. Even in similar climates and with similar design aims, constructive wetlands are being built differently using different materials and with different trees and plants planted. Although there's already research in this area, we still need a better understanding of how the differences between these designs affect treatment efficiency, how much greenhouse gas emissions are associated with them, and how they can be improved further to meet the ever more stringent discharge requirements. This is where my project comes in. This all comes together to provide the theme for this mini lecture, as overall we need to develop and improve technologies that will help achieve cleaner water in a greener way. So I've given a brief high-level overview of what's to come. Now let's look at it in more detail. I mentioned that we need to aim for cleaner water in a greener way, but why is it important? Well, globally we have many water crises at the moment, which are becoming more noticeable in the UK now, like when we have hosepipe bans in the summer. And according to UNICEF, 2/3 of the world's population already experience severe water scarcity. On top of this, the Department of Economic and Social Affairs, the people who deal with the United Nations Sustainable Development Goals that companies and researchers alike aim towards, have projections estimating that 2.8 billion people will lack safely managed sanitation in 2030. This means that we need a solution to clean water for reuse. Then we have greenhouse gases, where global emissions are still increasing despite the call from experts to reduce our emissions. The UK water sector currently contributes 4.2% to national emissions. It's gradually been reducing its energy-related carbon dioxide emissions. However, greenhouse gas emissions generated by biological processes, including wastewater treatment, still need to be tackled to ensure the worst effects of climate change don't come to fruition. This requires a greener solution for cleaning wastewater. As you may have heard from family members, friends, and the news, pollution from water companies in England has been increasing, and England now has some of the most polluted rivers in Europe. This puts our wildlife at risk and means we can't swim in English rivers, even ones that used to be bathing spots, without worrying about getting ill. Therefore, we need to ensure that treated wastewater entering our waterways is cleaner. Combining these needs together, you can see that we need cleaner water in a greener way. So now let's talk a little bit about my PhD topic. Previously I mentioned how constructive wetlands can help with climate change, but what are they? Constructive wetlands are areas of land built to mimic natural wetlands. Think of patches of water with reeds growing in them, how the edge of a pond or a lake looks in your local park, or how willow trees grow by the edge of rivers. These ecosystems are flooded or saturated with water either permanently or seasonally, and as a result, different biogeochemical processes occur. Wetlands store carbon, naturally clean flowing water due to these biogeochemical processes, and provide a natural solution to climate change. Due to this, constructive wetlands provide an innovative way to treat wastewater while providing environmental protection and conservation. Constructive wetlands planted with common reed have been used across Europe since the 1980s to clean water, and it is arguably the most successfully introduced new technology into the UK water sector in terms of the number and speed of systems built. This is no doubt thanks to the open collaboration across Europe, which led to rapid continuous improvement, shaping it into the technology that is still used today. However, recent research has shown that woody trees, like willow, could improve constructed wetlands' long-term performance and lifespan, and remove more carbon dioxide from the air. I'm lucky enough to be working with water industries in the Birmingham area to look at improving these existing constructed wetlands. My research focus is comparing common reed, which we currently use, and willow trees used by some Scandinavian countries in these constructed wetlands. I want to see if there's any differences between how the two wetlands perform when removing pollutants from the wastewater, if any changes occur seasonally. I also want to quantify the amount of greenhouse gases emitted, namely carbon dioxide, methane, and nitrous oxide from each type of constructed wetland during the treatment process, again, annually and seasonally. One pollutant in wastewater is ammonia, which can be added when people like you and me go to the toilet for a wee. Our urine contains a chemical called urea, which decomposes into ammonia. When ammonia enters rivers and lakes, bacteria strip oxygen out of the water to decompose the ammonia further, which in turn takes the oxygen away from plants and animals that need it to survive. A common practice to improve ammonia removal from wastewater is to aerate the constructed wetland. This provides more oxygen for the biological reactions to remove the ammonia. However, the aeration can also release more greenhouse gases. Alongside testing the comparison between the willow and reeds, I'm also interested to see how aeration affects the removal of the pollutants and the associated greenhouse gas emissions, again, seasonally and annually. A PhD is a big task, and it will take me between 3 and 4 years to complete, but it will be worth it. So far I've only completed 8 months of my PhD, but even in that time I've been keeping very busy. One key aspect of a PhD is that the produced research is new. Therefore, I've been reading lots of different literature that relates to my topic to see if it has been done before and to find the knowledge gaps so that I can tailor my research and ensure that what I do is in fact new. Initially, I wasn't sure what I was doing or how to proceed, so I used library resources and talked to other PhD students to understand how to go about finding literature so I wouldn't miss anything important. This resulted in me casting a wide net for looking at papers that have been published between 1972 and 2023 and contains keywords such as constructed wetland, common reed, and willow. Unsurprisingly, this gave me a lot of papers to look at, just over 2,000 in fact. Reading all these papers in detail would have taken an age, so I made a criteria of the papers I wanted to include and those I wanted to exclude. Then I read every paper's titles and summaries, compared them to my criteria, and only kept those that gave me what I wanted. I read all the papers in detail from this new list and extracted the information I needed. Overall, I reviewed 56 papers for reeds and 20 for willow, much less than where I started. Although I'm comparing reed and willow constructed wetlands, later testing on the effect of aeration required that I designed one of my aeration delivery systems ahead of time, as it would sit under the gravel, ready for when I needed it. I used more literature that I read to help me with my design and ended up doing 5 lots of testing to help. The last test I ran is pictured on this slide, and as you can see from the image, I managed to design a system that produced lots of bubbles. What you can't see is that I only managed to aerate half the wetland. Therefore, all I had to do was create a second one exactly the same to aerate the whole thing. As an advantage of my project is that I'm inheriting some already set up constructed wetlands from a previous PhD student. This reduced my workload as I only needed to set up 2 out of 8 of my wetlands, and I didn't need to make some design elements. Instead, I needed to copy the existing design so I could make the most of the ones that were already set up. That being said, it still wasn't easy as I had quite a few issues when trying to buy the components I needed. With perseverance and help from people at the university, I was able to buy all the things I needed. To create my wetlands, I needed to line the wetland containers with 3 layers of materials to make sure that it was completely watertight, add mesh at either end so that way I could have even water distribution, build a pipe network so that the water could be recirculated and delivered to my wetlands, fit one of my aeration delivery systems in one of the tanks, and fill the wetland containers with lots and lots of gravel. One thing researchers have done is use real sewage when doing their experiments. However, due to health and safety concerns and location restrictions, that isn't something I can do at the university. Therefore, I need to use synthetic wastewater when running my experiment. I've mentioned previously that I'm working with wastewater industries in Birmingham. Well, part of that is them providing me with insight and expertise I don't have, as well as providing real-world data that I can use to assist my experimental design. From this, we identified that existing recipes for wastewater weren't representative for real sewage in the area for the treatment stage I'm looking at. So I realised I need to design my own recipe. I analysed the data provided by the water industries in Birmingham and used their experience to determine what pollutant concentrations for my recipe I needed. Then, using this and existing recipes, I worked out pollutant concentrations for my recipe when I varied the amounts of different ingredients. I kept varying the ingredient amount until I got my very own recipe to meet the expected pollutant concentrations, at least theoretically. So I've mentioned I'm only 8 months in to a 3 or 4 year long PhD. It means I've got a lot of time left ahead of me, and here are some of the plans that I have for the future. As cool as it is, I've designed my very own wastewater recipe that's more representative of actual treated sewage at the final treatment stage. There's still more to be done. The next step is testing, where I plan to create small batches of the wastewater recipe and test the actual pollution concentrations to see how they compare to my theoretical calculations and the required concentrations. Based on these results, I'll need to adjust the recipe until the actual concentrations are close to the required ones. This initial testing will not only help me perfect my recipe, but give an indication of how easy it is to copy and how likely it is to vary between batches. Once a final recipe has been decided on, the recipe will need to be scaled up for 9 5,000 litre tanks. That's 45,000 litres of synthetic sewage, and I won't just be making it once. I've been working hard to set up the experiment, but some work still needs to be done. I need to wash the gravel, clean the collection buckets at the end of the wetlands so that water can be recirculated, plant the wetlands with reeds, buy pumps to stir the wastewater in the massive 5,000 litre storage tanks to keep it well mixed, insulate the pipes that transport the wastewater ready for winter to prevent freezing, and fit air stones at the beginning of each aerated wetland. Once I've done all that, I can finally start my main experiment of comparing the wetland with reeds, plants, to the wetlands with willows, trees. Then again, a little more testing is still required before I get in the swing of things. Initially, I'll start by taking water samples daily for 2 weeks. This way, I can see how much the concentration changes and how quickly. Based on this, I'll be able to work out how regularly the synthetic wastewater needs to be replenished and how often samples should be taken so they end up with an appropriate amount of measurements. Alongside taking water samples and testing them, I'll be measuring the nitrous oxide, methane and carbon dioxide emissions, the primary greenhouse gases, from the trees and plants at the beginning, middle and the end of every wetland twice a month. Once I have enough results, I'll be able to start analysing them and begin to process what the results mean when it comes to understanding and improving wastewater treatment wetlands. I hope you've enjoyed watching this mini lecture and found it interesting. To recap, these are the most important pieces of information I've covered and hope you take away with you. The climate emergency is exacerbating the water crisis and we need to tackle it. To prevent further damage to our environment and to try and repair it, this needs to be done in a sustainable fashion, a greener way if you will, by utilising more nature-based methods. Wetlands store carbon, naturally clean flowing water, and provide a nature-based solution to climate change. Creating constructed wetlands is a good way of harnessing the benefits of natural wetlands, as they can be used to treat wastewater more sustainably at a lower cost for decentralised households, acting as a potential cornerstone to providing cleaner water in a greener way. Lots of constructed wetlands are already in use across the world. Still, a better understanding and improvement of these wetlands' treatment efficiency and greenhouse gas emissions is required. This would allow more accurate emission predictions and push for constructed wetlands to meet ever more stringent discharge requirements, aiming for cleaner water. Finally, if you only take away one thing from this mini lecture, I hope it's the key concept and the primary theme of this entire mini lecture. And if it hasn't been made clear enough already, is that we need cleaner water in a greener way. Thank you for watching.